Good day and welcome to our today's class. Okay, today we are going to be looking at numericals on Carnot cycle. Okay, in our previous class, we have already talked about gas power cycles, whereby we considered the definition and further explanations on Carnot cycle. So we are going to be solving some numericals under Carnot cycle. So our first example says a Carnot engine working between 400 degrees Celsius and 40 degrees Celsius. It means that 400 degrees Celsius, of course, is the maximum temperature and 40 degrees Celsius is the minimum temperature. It produces a work of 130 kilojoules. Now we are asked to determine the engine thermal efficiency, the heat added, the entropy changes during heat rejection process. So first thing first, I am going to be drawing, of course, the PV diagram and the TS diagram of the Carnot cycle. So this is what we are going to be doing. I'm going to be drawing my PV diagram first. So I have a straight line here. I also have another straight line here representing my volume. So of course, I have here to be what? P. I have here to be V. And of course, for my stages here, what do I have? This will be stage 1, this will be stage 2. Here I have stage 3, and here I have stage 2. So I can join, of course, here I'm going to be, this will represent my volume as stage 3. This will represent my volume as stage 4. This will represent volume as stage 2. And this will represent my volume as stage 1. So this is what I have. Now from stage 1 to 2, what do we have? We have isentropic expansion. From stage 2 to 3, we have adiabatic expansion. From 3 to 4, we have isothermal compression. And from 4 to 1, we have adiabatic compression. Now it means that what? For stage 1 to 2 and for stage 3 to 4, what I have is isothermal expansion and compression. So I can just represent it by com sp for expansion. So what do I have next? From 2 to 3, of course, we know it's adiabatic, it's a reversible adiabatic process. From 4 to 1 is also a reversible adiabatic process. Of course, this for 2 to 3 is expansion and 4 to 1 is compression. So what do I have? I can just indicate here. Of course, I need an arrow here. So this will be what? Isentropic. So this is what I have. So I'm just going to be tracing my pressure line. Of course, here is P1. Of course, I have P2 here. It's P2. For stage 4, I have P4 here. It's P4. And lastly, I have P3. Of course, this is P3. So next, I'm going to be drawing my TS diagram. Of course, this is PV diagram. Next, I'm going to be drawing my TS diagram. To draw my TS diagram, of course, I have a straight line here, representing temperature, and at the bottom, I have a straight line representing entropy. So this is what I have. So of course, you know, on the TS diagram of a Carnot cycle, the stages are represented by straight lines. So I have a straight line here, I have another here, I have another line here, and lastly, course. So of course, this should be 1, 2, 3, and 4. So I can trace it down. Of course, I'm going to having a temperature here, but of course we have T4 to be equal to T3. Of course, you can see that the temperature along stage T, stage 3 to 4 is constant. This is what we have. Now, coming here, we are going to be expressing rather our data given. We we have data given. Okay, so this is our data given are in the question. Of course, you know that this line traces down here, and we also have coming down here. Of course, so from here, what do you see? You can see that from 2 to 3, entropy is constant. So S2 is equal to S3, and S1 is equal to S4 here. So this is what we have. So next, what do we do? Of course, I say we are going to be listing our data. So for our first temperature, which is 400 degrees Celsius, it will be the maximum temperature. Of course, the maximum temperature occurs at this point because this is the point where heat is being added from T1 to T2. Okay, so our maximum temperature, we can say Tm equal to what? Equal to 400 degrees Celsius. So if I convert 400 degrees Celsius to Kelvin, I'm going to be adding 273 to it. Of course, this will be equal to 673 Kelvin. And of course, we know that our at maximum temperature T1, of course, is our maximum temperature, which is equal to T2. So this value here is equal to T1, and it's also equals to what? Equal to T2. So next, we are going to be expressing, of course, we know that our minimum temperature, so I can say here max, max, and I can call here min. So our minimum temperature, of course, is 40 degrees Celsius. Of course, if I convert 40 degrees Celsius to Kelvin, it will be nothing but 313. Of course, it will be nothing but 313 Kelvin. So of course, and you can see here my minimum temperature, of course, it can be T3, it can be T4, where T4 is equal to T3. So this is equal to T4 and it's equal to T3. What do I have next? I have work done. We're told that this Carnot engine produces a work of what? Of 130 kilojoules. So my work done equal to 130 kilojoules. What do I have next? Okay, that's all. So we are asked to find first the what? The engine thermal efficiency. So we have engine thermal efficiency. Now, from our previous video, we have showed the efficiency of a thermal of a Carnot circle. Of course, the efficiency of a Carnot circle is nothing but what? Is nothing but the maximum what? Maximum temperature minus the minimum temperature all over what? All over the maximum temperature. So this is what we have. So what do we do next? Of course, this formula is nothing but, before I move further, of course, we know that our maximum temperature is equal to T1 and of course equal to T2. And our minimum temperature is equal to what? It's equal to T4 and of course equals to T3. So I'm going to be using T1 and T4. So this formula can be written as T1 minus T4 all over what? All over T1. Next, what do? We are going to be substituting our values and we get the efficiency of the efficiency of a Carnot cycle NTH will be equal to T1. Our T1 is nothing but what? Is nothing but 673 minus what? Our T4, which is the minimum temperature, is 313. I have it to be all over what? All over T1, which is our maximum temperature, which is 673. All you have to do is just to press this in your calculator. You have an efficiency, of course, to be 0.535. So 0.535, which we will multiply by 100%. So our efficiency is equal to what? 3.5%. So this is the thermal efficiency of this Carnot engine. This is the thermal efficiency of this Carnot engine. Of course, working between 400 degrees Celsius and 40 degrees Celsius. Next, we are asked to find the heat added. we are asked to find the heat added. So just going to write for item 2, we are asked to find the heat added. So we are asked to find the heat added. Now, make no mistake, make no mistake, at this point, we are having what? We are having heat addition. I can say Q A to be heat addition. The temperature of heat addition is not the same as the heat addition, because in most cases people mistake the temperature of the heat added to be equal to the heat added. Of course, they are not the same. So we have our efficiency to be equal to what? To be equal to work done all over heat added. Of course, we know that the temperature at which heat is added to this circle is nothing but what? The maximum temperature, which is T1, and of course, which is equal to T2. So next, what do? We'll make heat added the subject of this relation. So it means that I'm going to be denoting heat added with H multiply HA rather. So I have HA multiplied by my efficiency to be equal to what? Work done. And of course, heat added will be equal to work done all over what? All over efficiency. So this is what we have. So next, we are going to be substituting our values to get the heat added on the Carnot engine. So what do we have? We have HA added to be equal to what? To be equal to work done all over what? All over efficiency. So our work done from the question is 130 kilojoules all over our efficiency. Of course, our efficiency is nothing but 0.535. So if you press this in your calculator, you'll be having your heat added to be 243, of course, kilojoules. So this is what we have. So next, our last question says the entropy changes during heat reduction process. So we need to find the entropy change during heat reduction process. Question 3 says the S, of course, is our change in entropy. So now, from second law of thermodynamics, we know that change in entropy, from second law of thermodynamics, we know that Q, which is heat, is nothing but what? Is equal to T dS. From second law of thermodynamics, we know of this relation. So what do we do next? In view of this question, we are going to be having Q to be what? The heat rejected. So we can put Q substitute R to be equal to what? T. T now will be our temperature rejected. But of course, you know that our temperature rejected is nothing but our minimum temperature, which occurs at this point. So we have QR here, and of course it's equal to what? It's equal to 40 degrees Celsius, which we have converted to 313 Kelvin, and it's equals to T4. It's also equals to what? It's also equals to T3. So we can denote that by T4 here. Our change in entropy, of course, at this point will be nothing but S3 minus S4. We have S3 minus S4. So this is what we have. So now what are we looking for? We are looking for our change in entropy. So we can make change in entropy the subject of this relation. So this will be S3 minus S4 and S3 minus S4. So of course, what do we have? Now we are going to be dividing by T4. We are going to be dividing by T4. Of course, we want to make our change in entropy subject. I have T4 here, I have T4 here. So of course T4 will go with T4, and S3 minus S4 will be equal to QR, which is our heat rejection, all over T4, which is our minimum temperature. So what do I do? I'm going to be substituting my values. I'm going to be substituting my values. Of course, I have the value for T4, but we don't know our value for QR, which is our heat rejection. But from work done, we know that work done is equal to what? Is equal to heat added minus heat rejected. Of course, we can use H and of course we can use E. So I can say QA minus QR. So of course, work done is equal to this. So what do we do? From here, we can find QR. Of course, we know our value for QA. We have gotten that already. So work done will be equal to QR rather, which is our heat rejection, will be equal to what? QR will be equal to heat added minus what? Minus work done. So this is what we have. So it implies that QR will be equal to what? Will be equal to our heat added minus heat. So what we are going to be doing, we are going to be substituting our values. We have 243 for our heat added minus our work done, which is 130. Implies that QR is equal to what? QR will be nothing but so and get the value for QR. So I have my value for QR to be 113. Ensure you press your calculator. So what do we do next? We are just going to be substituting our value here and we have the change in entropy, of course, during heat rejection process. So I'm going to wipe this side as we substitute and get our change in entropy during heat rejection process. So I have S3 minus S4 to be equal to what? 113 all over what? All over T4. Of course, what's the value for T4? It's nothing but 313. Of course, press this in your calculator. What will be our change in entropy? It will be 0.361 kilojoules per Kelvin. 0.361 kilojoule per Kelvin. Of course, this is our value for change in entropy during heat rejection process. So, of course, I hope you understand and enjoy this video. Stay tuned for more numericals on Carnot cycle. Thank you.